Again, our valence electron is going to be the electron in the outermost filled electronic level of your atom. Let's try something like carbon. If we look at carbon, carbon's got 6 protons in its nucleus. All right, so it's going to be balanced off by 6 electrons. However, if you remember from your atomic structure class, that lowest 1s level can only fit 2 electrons into it. All right? We need to fill the remaining 4 electrons into a higher energy level. All right? So we can say that carbon has a total of 4 valence electrons. Does that make sense? Okay, again, this is the business end of the atom. This is what the atom is going to be using to form bonds with. Going to be using to form bonds. Well, the periodic table is pretty helpful in that regards in trying to figure out how many valence electrons an atom has. Right? If you look at your periodic table, you're going to see a group number above each column.
Right.
The group number that chemists have been traditionally using for decades is represented by these Roman numerals. So carbon is said to be in group 4. Right? I'm not going to get into what the 4A versus 4A, 4B means. Right? But in 1988, the UPAC, or the IUPAC, decided, you know what, let's get rid of those Roman numerals that work so well for all of us. All right? Let's name the groups from 1 to 18, sweeping away the Roman numerals that we use to determine how many valence electrons we have in each group. Right? Being very helpful to us as chemists. So I don't know what type of periodic table you're going to get for your remaining exams. I know for your pre-exam you didn't have a periodic table. I apologize. But for your remaining exams you will have a periodic table. The periodic table may or may not have these Roman numerals on there. And these Roman numerals are how we tell how many valence electrons each atom has. So if you have a periodic table that is just listed 1 to 18, what I want you to do is look at your periodic table, close your left eye, and just ignore the 1 that's in front of the IUPAC number. All right? So group 13 really just has 3 valence electrons. Group 14, all right, just ignore the 1 in front of the 4. You have 4 valence electrons. Group 17, just ignore the 1. You have 7 valence electrons. All right? So just look at your periodic table, and it's going to give you a lot of information that you need. Does that make sense?
Yeah.
All right. So that means if I asked you, ignore these metals, we're not going to ask you about these metals. This gets a little complicated when you count the number of electrons on metals. But if I were to ask you how many valence electrons arsenic had, AS, what would you tell me? 5. All right, that's not a problem. How about bromine? 7. Yeah. How about argon?
8.
Hey, that's not too bad. All right. Question, sir? No? Okay. Any questions on this? So this is how we determine the number of valence electrons that are available to an atom. All right. Let's talk about the octet rule. I don't know what's happening there. Okay, we're good with the concept of valence electrons. The octet rule is a rule that we have, and it says that the tendency of an atom to achieve a configuration wherein it has 8 electrons is going to lead to a stable system. So that's called the octet rule. Now what's this based on? This is based on the idea that there are these atoms that we just can't get to react. Does anybody know what we call these atoms here in group 8? The noble gases. Right? They used to be called the inert gases, right? People thought that we couldn't get these things to react. And for the most part, they don't react. Helium doesn't react. Makes your voice sound a little bit funny when you inhale a balloon with helium, right? But it doesn't really form compounds all that readily. Well, in the 1960s, they figured out that they can form compounds with krypton and xenon and stuff like that. But in general, these things still don't react. Well, why is that? Well, if we look at the electronic structure of neon, right? It has an atomic number of 10, so it has 10 electrons. You give 2 of those electrons to your first energy level, right? And then you fill in your second energy level with the remaining 8 electrons. All right? This turns out to work for all of the inert gases, all of the noble gases. They all have 8 electrons in their valence shell, and they're relatively unreactive. Does that make sense to everybody? So chemists had devised that other elements on the periodic table would like to achieve the electronic configuration of those noble gases. All right, and they would react as such to get a configuration that the noble gases possess. Any questions on that so far? All right, so that's especially true for atoms in our second row. All right, so if we go back here to carbon, how many valence electrons does carbon have again? 4. All right, so let's change this to carbon. So if carbon has 4 electrons in its valence level, how many electrons would it like to have the configuration of a noble gas? How many more would it want? 4. Yeah, carbon wants to get 4 more electrons. Pardon? Or lose 4, right? And we'll talk about atoms that like to do that. It needs to get 8 electrons in that outer valence shell. Carbon more likely goes up to 8 rather than loses them. Things over here like beryllium and lithium, they tend to lose them to go down. All right, does that make sense so far? So how many bonds would carbon form if it needs 4 electrons to form an octet? 4 bonds. All right. Let's try this with something else. How about oxygen? How many valence electrons does oxygen have? 6, right? It's in group 6. You can use the Roman numeral or just ignore the 1 in front of 16. All right, so that has 6 electrons in its valence shell. How many does it need to obtain an octet? 2. So how many bonds would oxygen normally form then? 2 bonds. That makes sense though, right? Because what's the molecular formula of water? H2O. Right? So you have an oxygen that's connected to 2 hydrogens. And we're going to see how we can put these things together in valid Lewis structures today. Is everybody on the same page with me so far? Yes. All right. Is everybody falling asleep because I am incredibly boring and this is not fun at all? Is anybody falling asleep because we had turkey for lunch? No tryptophan? All right, excellent. I know they had ham today, so we're good. Yesterday was rough. They had turkey. All right. So we're all good on the non-reactivity of the noble gases. And this is chemistry cat. I hate telling noble gas jokes. There's never a reaction. This is chemistry cat. If you want to tell bad jokes in chemistry class, chemistry cat is a great venue for it. I hear that he's Russian. I really don't have any evidence to back that up though. But there's this meme generator online where you can go in and create your own chemistry cat bad jokes. And so, you know, whoever put this cat in a bow tie and a pair of glasses was an absolute genius. But anyway. All right, so we're good with valence electrons. We're good with the octet rule. Now let's talk about different types of bonding. The one type of bonding as an organic chemist that I despise is ionic bonding. And we'll talk about that first briefly. All right. An ionic bond forms when you have atoms coming together of vastly different electronegativities. Is everybody familiar with the concept of electronegativity? All right, it's a tendency of an atom to attract electrons to itself. We know fluorine is the most electronegative atom. We'll talk more about that in the next class when we talk about polarity. But let's say we have a lithium atom and a fluorine atom come together. They meet at a bar. Lithium says, hey, I've only got 1 valence electron. There's no way I'm ever going to get to an octet around me. And fluorine says, hey, lithium, I've got 7 electrons in my valence level. I could use just 1 more electron to become a noble gas configuration, to have a noble gas configuration. And then lithium says, well, hey, I really don't need this extra electron. It's really dragging me down. If I lose this 1 electron that I have in my valence level, I'm going to go down to have the configuration of helium with having 2 electrons in my highest occupied energy level. Does that make sense? We sort of need the periodic table to look at, and I was sort of thinking that since this is a science building, we'd have a chemistry periodic table on the wall here, so I'm just going to do my best and draw up a periodic table here. This is the 7th time that I've taught this, and this is the 7th time that I have not placed helium correctly. Do any of you make your students learn the elements of the periodic table and sing songs with them? Yeah. Yes. Hydrogen, helium, lithium, beryllium, boron, carbon, nitrogen, oxygen. It's a great song. I think we learned up to like 25 or thereabouts. And there's a Tom Lehrer song with the elements, which is pretty good too. And then somebody recommended They Might Be Giants song that I've never heard before about the periodic table. But that's a fun way to talk about them. Our group numbers. Again, I'm using the traditional values rather than the new and improved values that the IUPAC or the UPAC is trying to enforce on us. Okay? So if we look over at lithium, how many valence electrons should lithium have according to our periodic table? And fluorine has how many? 7. All right. So when they get together, lithium says, all right, if I give this one up, I'm going to go back to the configuration of helium, having 2 electrons in my lowest energy level. And if you remember from your atomic structure class, you'll realize that that energy level only needs 2 electrons to be filled. Fluorine, on the other hand, gets the 8th electron. And so it now has the electronic configuration of neon. All right. This is called an ionic bond. All right. One atom is coming up to the other atom and straight up stealing an electron. You're forming a positive ion, a cation, which is this lithium, and this fluorine is a negative ion called an anion. All right. This is an ionic compound. Okay. We often refer to these as salts. All right. What's another salt that we use every day? Probably had too much of it at lunch today. Sodium chloride, right? Where's sodium on the periodic table? Below lithium, right? If it's below lithium, how many electrons does sodium have? 1. How many valence electrons does chlorine have? 7. So if sodium and chlorine, which is beneath fluorine here, get together, the same thing's going to happen. The sodium atom is going to give 1 electron to the chlorine. Chlorine's going to have an octet. And our sodium will have the electronic configuration of a noble gas. All right, so everybody's going to be happy. This is an ionic bond. I'm not terribly interested in this, but this sort of shows you the idea that we're going towards. We want our atoms to have octets. Is everybody with me? Yes. All right, good. I don't know what happened there. But I have another terrible chemistry joke. My chemistry teacher threw sodium chloride at me. That's a salt. Get it? It's a salt because I threw the sodium chloride at you. All right. I'll stop, I promise. No more chemistry cat. All right. Let's talk about covalent bonds. And covalent bonds are bonds wherein our electrons are not going to be ripped off and stolen by other atoms, but our electrons are going to be shared. Right, so covalent, we're co-sharing these valence electrons. So our simplest molecule that we can create with this comes from our 2 simplest atoms. If we take 2 hydrogen atoms and we bring them together, and I broke my chalk, each comes to the table with 1 valence electron. They can share those 2 electrons like this in a bond, forming the H2 molecule. All right. This hydrogen is not stealing the other hydrogen's atom. It's not an ionic bond. This is a covalent bond. All right. This is really where these solar system type of diagrams break down. All right, so if this is our rudimentary solar system type diagram here, all right, these 2 hydrogen atoms, not drawn to scale, are approaching one another. All right. And as these 2 nuclei get closer, these are positively charged, right? What happens when you bring 2 positive ends of a magnet together? They repel one another, right? All right. Well, you can't bring them together. It's going to be impossible to bring these 2 positive protons together, unless you have a super collider or something like that, which we don't. But if you have these 2 electrons here, we can use those electrons as the glue that holds these 2 nuclei in within the distance of a bond. A molecular orbital is not one of these solar system type things. A molecular orbital is a location in space where the probability of finding an electron is greater than 0. All right, so it's not these nice looking orbitals here. When you form a molecular orbital, you're saying that the probability of finding an electron in the space between those two nuclei is going to be greater than 0. Well, what does that really mean for us? What does that do for us? These two positive nuclei are going to be repelling one another, right? But if you put two electrons in here, right, this positive charge is going to be attracted to an electron, and the other positive charge is going to be attracted to an electron. They're sharing those electrons. They're balancing out those charges. And that attraction between those two opposite charges overrides the repulsion that you'd get as you brought two positive nuclei together. All right, there's a nice chart in most college textbooks that show the energy changes as a function of internuclear distances. I'm not going to talk about that here, but you get to a sweet spot where you have an energy minimum, and that's where your bond is. And that's where your bond distance is. So this is really what's going on. We're having a space between the two nuclei wherein the probability of finding electrons is greater than 0. Does that make sense? Okay, so that's what we're really saying when we're drawing this covalent bond forming. Okay? We can do it with more complicated atoms, with chlorine here. All right, how many valence electrons does chlorine have based on our periodic table? 7. All right, if you bring two chlorine atoms together, they each have an electron that they can share with one another, just like the hydrogens did above. So you can have a situation where these two electrons will be shared equally between those two chlorine atoms. That's going to be a covalent bond. Does that make sense? All right, let's get more complicated. Let's do something fun. Does anybody know what CH4 is? Methane. Where do we get methane from? Cows. Yes, cows, lots of places. But cows is one of the people. Yes, some people. All right. What does methane consist of? CH4. We have a carbon. How many valence electrons does carbon have? 4. It's 4. If we have 4 hydrogen atoms, how many valence electrons do they bring? 4. 1 apiece. We can arrange those atoms such that the carbon will share all of the electrons that the hydrogens bring. Look what we've done here. How many electrons are around this carbon now? 8. How many electrons are around each chlorine above? 8. All these atoms here have octets, or the electronic configurations of noble gases. That's exciting, right? I'm sort of, yes, question.
When you were diagramming the hydrogen gas, the diagram that I have for my students shows it more of like a dumbbell-shaped electronic cloud. Is that incorrect?
No, no, it's not incorrect. It will be the overlap will be more dumbbell-shaped than how I've drawn. I'm just drawing a. Yes, that's we can't precisely know the location of the electrons of a certain energy level. So all we're saying is that there's a probability here. That's what we're trying to say by the molecular orbital.
So the highest probability is between the two.
Yes.
The lower probability.
Yes.
Would be the
There's a from quantum mechanics. There's a wave function that you can solve, and you can find what the okay. Using that, you can draw out what these molecular orbitals actually look like. Okay. We're not going there today.
That's fine.
Okay. Nope. Good. All right. So that sounds pretty simple so far, right? These are going to be called dash structural formulas. All right. Because we use dashes to represent these electrons. It's really a pain just drawing these dots all the time. I mean, it sort of relieves a lot of stress if you can hit the snot out of a chalkboard every once in a while, but in practice it gets to be a little distracting. So we use these dash structural formulas to draw these molecules a little quicker. These are often called Lewis structures, and the scientist I have up here is Gilbert Lewis, who's from the University of California at Berkeley, and he's the scientist the chemist that put these things together. And it's kind of sad. He was supposedly on the short list for the Nobel Prize about 30 times, and He never was awarded the Nobel Prize. But every chemistry student that learns about structure learns about Lewis structure. So it's the foundation for what we're talking about. So what I have right here is just a menu of where we're going. Don't freak out about these structures right now, but this is the type of structures you're going to be able to put together. As I said, I'm an organic chemist, which means I'm the worst person in the world. So I have some organic molecules up here. I have ethane. All right, it's just one more carbon than methane. All right. We have two carbons bound together by a single bond. We have things that we'll refer to as double bonds, where there are going to be a total of 4 electrons shared in the internuclear space, well, shared somehow between these two carbons, not necessarily internuclear. We can have triple bonds, where there will be a total of 6 electrons joining the 2 carbon atoms. All right. Nitrogen, it's the main component of our atmosphere. That's a triple bond between 2 nitrogen atoms. And we can even have ionic species. This is ammonium, NH4, and there's a positive charge on that. So we're going to figure out, how we know that there's a positive charge on that nitrogen. That's the formal charge component of what we're going to talk about today. All right, so this is where we're going. Is everybody happy with that? All right. Now, Lewis structures are a human-made device. Right? So these are an approach to understanding what the structure of these molecules look like. So they're not by any means going to be perfect. But Lewis structures, or as Gilbert Lewis would call them, me structures, have a number of different rules that we have to follow. All right? Lewis structures, we already know, only use valence electrons. Okay? We already know, too, that the number of valence electrons on a neutral atom is going to be equal to the group number on the periodic table. For example, carbon has 4. All right, nitrogen has 5, oxygen has 6. I can draw in a couple more atoms here. Okay. When we look at molecular structure, however, we're not always going to be assigning or coming up with Lewis structures for neutral molecules. So we might have to figure out what an anion or a cation looks like. An anion is a negatively charged ion. A cation is a positively charged ion. What we're going to be doing, we're going to be totaling up the number of valence electrons in each of these structures. And if we have an anion, we have to add an extra electron to our total electron count. It makes sense because your molecule is negatively charged, right? So that means it picked up an extra electron somewhere. Okay? It stole it from a very electropositive element. Okay? If your structure is a cation, it lost an electron somewhere to another electronegative element. Right? So we're going to have to subtract an electron for each positive charge. And I'll show you what I mean when we do examples here. Our goal here, at least initially, is to give each element in our molecule the configuration of a noble gas. All right? Atoms in our second row of the periodic table, our second period, are going to want to have 8 electrons around them. Hydrogen, again, only needs 2 to have an isoelectronic configuration with helium. Right, to have helium's electronic configuration. Does that make sense? All right, so let's try a simple one. Let's try methyl fluoride, CH3F. Okay, so when you have to do something like this, I just want you to write that structure down at the top of your paper. Write down CH3F. We're going to play this like a poker game. Each atom is going to be bringing a certain number of valence electrons to the table. All right. Carbon. How many valence electrons does carbon bring with it to the table? 4. Write a 4. How many valence electrons does hydrogen bring to the table? 1. And we have 3 of them, so we're going to be adding 3 hydrogens, right? Make sense? How many valence electrons does fluorine bring to the table? 7. Perfect. All right, now I'll let you know a little secret. At the University of Scranton, I volunteer for the family weekend, and I volunteer as a blackjack dealer on casino night. And I can't count to 21 to save my life. So if I make math mistakes, please let me know. So 4 plus 3 plus 7 is roughly 14, I think. Okay. So roughly 14 electrons in this molecule. Okay? Is everybody with me there? All right. We're halfway there. 4 plus 3 plus 7. We've got a carbon with 4. We have 3 hydrogens. They bring 1 apiece. And fluorine brings 7. Now comes a little bit of trial and error. If you're not familiar with how these structures are put together, you may get it wrong the first attempt. But we already said, how many bonds does carbon form? 4. Right? So that's sort of a help in the right direction. We have 5 atoms in this molecule, so carbon probably forms bonds with the remaining 4. And I've sort of tipped you off in how I've written it here. I've put the 3 H's right after the carbon. So I can say that this carbon will likely form bonds with these 4 atoms. And now I need to start distributing out the valence electrons that I've collected at the beginning of the game here. All right, and I have to use those electrons to form bonds. I'm going to draw dashes between the elements, and that's going to represent 2 electrons in a bond. All right, so if I have 14 electrons, put 2 there, 2 there, 2 there, and 2 there. All right, I've formed 4 bonds from carbon. How many electrons do I have around the carbon right here? 8. Is carbon happy? Yeah, carbon's happy. It has 8 electrons around it. It has the same electronic configuration of neon. What atom is not happy so far? Fluorine. Why? It only has 2. It needs 6 more. Well, 14 minus 8 should give you something about 6. Right? So that's pretty good. That means that we can distribute these 6 electrons as non-bonding electrons around the fluorine. I always, always, always draw my non-bonding electrons. You're never going to lose track of your structure that way. You're going to know how these things are going to react. Don't just write these things up here and forget them, especially on these heteroatoms, on these atoms other than carbon. Always, always, always draw in your non-bonding electrons. Well, does fluorine have an octet now? Yeah. So it looks a lot like the electronic structure of neon. So that's a full and valid resonance structure for methyl fluoride. Is that so far so good? All right. Oh yeah, we're going to do a lot more. Questions on this so far? Good. Let's do harder ones. All right, let's... Well, I'll ease you into it. How's that? I'm not an evil person, I promise. Okay, let's... an evil scientist, yes. Well, I'm an evil organic chemist, which must mean that I have gallons and train cars full of methylamine. So let's do methylamine. All right, the structure of methylamine is CH3NH2. All right, so we're going to do the same thing that we did before. I'm making it worse. I think we're good for now. If it gets hot again, I'll turn it back on. All right, the structure of methylamine is CH3NH2. So we're going to do the same thing that we had done before, right? We're going to tally up how many valence electrons this thing brings to the table. So carbon brings how many?
4.
Hydrogen, 3 hydrogens bring how many? 3. Nitrogen brings how many? 5, very good. It's in the 5th row over there, or 5th column. And these last 2 hydrogens bring how many? 2, perfect. All right, so 4 plus 3 plus 5 plus 2 is 14 again, right? I didn't do that intentionally. All right, so we have 14 electrons. Again, I've drawn this molecule suggestively. I've put those 3 hydrogens after the carbon. So that means that these 3 hydrogens are probably going to be connected to that carbon. All right, that's a condensed molecular formula where we try and group together the atoms that are bonded to one another. All right, so I can say right off the bat, this carbon's connected to those 3 hydrogens. How many electrons have I used to connect this carbon to 3 hydrogens? 6 electrons, very good. We need to have 8 around carbon, so it's probably connected to something else here. What do we think? The nitrogen. All right, so I've used 8 electrons. Carbon has 8 electrons around it. Is it happy? Yes. I still need to distribute these 2 more hydrogens. All right, so where do you think they go? On the nitrogen. Very good. All right, how many electrons have I used in total now? 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. I have 2 left, right?
Double bond on hydrogen and 2 unbonded on nitrogen. No.
Does every atom have an octet so far?
No.
Nope, no, can't. Don't double bond the hydrogens. That one's bad. What doesn't have an octet?
Nitrogen.
The nitrogen, right. So we can put 2 non-bonding electrons. Doesn't matter how you draw them. I could have drawn this. Yep, I could have drawn it just like that. For these Lewis structures, doesn't matter. On Friday when we talk about the 3D shape, it'll matter more. Okay, good question. Does that make sense to everybody? All right. So we've gone from this molecular formula to this Lewis structure. All the atoms here are happy. They have the configuration of a noble gas. Questions so far? All right, let's do OCl2. OCl2. How many electrons come to the table with oxygen? 6. How many come with chlorine? There are 2 of them. Correct. So we have 14. That comes from 2 chlorines. Yes. All right. So don't lose count of your valence electrons. This is a neutral atom, so we don't need to worry about adding or subtracting any, or neutral molecule, so we don't need to worry about adding or subtracting anything. So 6 plus 14 is about 20. Okay. So now you can start to take advantage of your familiarity with chemistry. We know oxygen forms 2 bonds with water, right? So it's probably going to form 2 bonds here as well. So we can go through trial and error and say, all right, we're going to use 4 electrons to join these 2 chlorines to the central oxygen. Does that make sense? Mm-hmm. All right, so we've used 4 electrons out of these 20. All right, so 4, that's 16 electrons. What I like to do then is just dump in the rest of the electrons into your system. All right, so I'm going to start filling up the octets on all of these atoms. All right, that's 16 electrons that I've used now. Does every atom here have an octet?
Yes.
Yeah. Is this a valid Lewis structure? Yeah, that's not too bad. All right. Let's do, well, tell you what, let me talk about, you see I have a couple of anions up here, right? You can't really do anions justice until we talk about formal charge. So let's move into talking about formal charge before we get anywhere else. All right, is everybody with me so far? This isn't so bad, right? For those of you with a, do not have such a strong of affinity for chemistry as I do, this is, this goes down all right. Okay, let's talk about formal charge before we do more examples. We'll find for that many of these molecules that we want to draw structures for, they're going to be ions of some sort. So these structures are going to be incomplete until we assign in that molecule where the center of that electron excess is or that electron deficiency is. All right. Formal charge, again, it's a human-made device that we use to keep track of these charges. All right, these ions in nature don't know, hey, I've got a formal negative charge on my oxygen here. It just knows where the electron density levels are or where electron deficiencies are. There are many ways to calculate formal charge. The easiest way that I use to do it is with this formula. And this is, again, where the periodic table is going to help you out. Your formal charge is going to be equal to your group number on your periodic table, the old-fashioned ones, the ones that work well, right, minus half of the shared electrons around that atom. That means all the electrons in bonds around that atom, minus the number of unshared electrons around that atom. Okay. Let's go through an example for this. if we're doing an ion, the sum of the charges on the atoms, or even for a neutral molecule, the sum of the charges on the atoms must equal the overall charge of the molecule. So let's try ammonium, NH4. Positive. You can draw a circle around your positive sign. You don't have to draw anything around your positive sign. You can draw a square if you want to draw a square. It doesn't really matter. I like to draw circles around my positive sign. Let's do the same thing we've done before. How many valence electrons do we have in this species? Nitrogen brings 5, and 4 hydrogens bring 4. We have, however, a positive charge on here. So we need to subtract an electron from your total valence electron count. Oops. That makes sense, right? Because if it's positively charged, it's lost an electron somewhere. So 5 plus 4 minus 1 is equal to 8 electrons. The only possible way that you can put these things together is by putting 4 protons, or 4 hydrogens, excuse me, around that nitrogen. Okay. Does nitrogen have an octet here? Does it have an octet? Yeah. It has 8 electrons around it, right? This bugs you though, doesn't it? Because didn't we say before that nitrogen forms 4 bonds, or 3 bonds, excuse me? Yeah. And remember we had that lone pair on the nitrogen before? So this should bug you. This should bug you real bad, right? But this is where formal charge comes in. Formal charge is going to account for the uneasiness that this NH4 makes us feel. So we're going to go through each of these atoms here and calculate whether or not an atom is electron deficient or has an electron excess. If it's positively charged, you're probably going to have an electron deficiency somewhere. Okay? Let's just do hydrogen just for the sake of it. Hydrogen is in the first group, right? So that's going to be the group number, which is 1. This is using this equation up here, minus half of the shared electrons around a hydrogen. So this hydrogen shares how many electrons? 2. So half of that will be 1. So 1 minus 1, and then minus the number of unshared electrons on this hydrogen. Does it have any unshared electrons? No. So 1 minus 1 minus 0 is equal to 0. All right, that hydrogen's neutral. Thank goodness, because if the hydrogen was positive, we've had a problem. Okay. Does that make sense? So let's do, and can we all agree that we'd get the same result for the remaining 3 hydrogens? Good. Let's do this nitrogen. What group is nitrogen in? 5. How many electrons does it share around it right now? There are 8 around it, right? 1, 2, 3, 4, 5, 6, 7, 8. So half that number is 4. How many electrons are unshared on it right now? None. So 5 minus 4 minus 0 is equal to plus 1. All right. So this is telling us that there's a positive 1 charge on this nitrogen. And you can indicate that with a little positive sign. You can circle the positive sign, or you can just leave it as a regular positive sign. That goes in stark contrast to the methylamine that we had up there before, right? The methylamine that we had up there before had nitrogen with 3 bonds to it and a lone pair of electrons. Okay. This nitrogen doesn't have a lone pair of electrons all to itself. It's sharing what used to be its lone pair with another atom. That's why it's positively charged now. Right? The 2 electrons that it used to have to itself, it's sharing with another atom. So it has an electron deficiency on that atom, on the nitrogen here. All right, this is why we need formal charge. It's a cop-out just to say, all right, overall there's a formal charge on this molecule because there's a formal charge on that molecular formula. We need to know where that positive charge is. Does that make sense? Any questions on this so far? Okay, let's try some more. All right, this is just sort of walking you through it. All right, let's try something a little bit more difficult. Let's try nitrate. me see if this air conditioner is behaving anymore. We showed the air conditioner who's boss. All right, nitrate, NO3 minus. So let's do the same thing we did before. Even though this looks a little bit more exotic, it's really not a problem. How many electrons does nitrogen bring to the table? I'll just speak louder. Nitrogen brings 5 electrons to the table. How many does oxygen bring? 6. And there are 3 of them, right? So that's about 18. There's a negative charge on this, so what do I need to do? To add 1. It's negative. It picked up an electron from somewhere, right? Maybe if I'm gentle with this air conditioner, we'll stop doing this. Ah, I got it. Yes. All right. So 5 plus 18 plus 1. What's that? That's 24. 24 electrons. Everybody with me? Cool. All right. NO3. Again, you can have some trial and error here. People might put the atoms together in the non-optimal way at first. All right. But as you become more familiar with these molecules, you know, nitrogen usually likes to have, 3 bonds. So let's start there. Hey, it didn't in the last one, so we might be wrong. But you got to start somewhere. How many electrons have I used so far? 6. All right. So I need to use 18 more. I like to approach these in a systematic way. I'm going to put in all of my electrons into the system, even if I might be wrong on my initial attempt. But I want to put all the electrons in there before I start guessing as to where there might be multiple bonds. Okay? So what do I mean by that? If I have 18 electrons left, I'm going to try and fill up the valencies on all of my elements. All right? I like to start with usually the more electronegative element, but that's just a personal preference. It's not necessarily a rule. So I'm going to fill in the valencies on all of the oxygens. And that means I'm spent with my total electron count. Do all of the oxygens have an octet? Does nitrogen? Can I just give it 2 more electrons? No, I'm all out of chips. I don't have any more electrons that I can give to this system. Right? Does everybody see that? I can't borrow some electrons from my friends. It's just not allowed. Get your hand cut off for that or something like that. Okay? So I've spent all my electrons, but I don't have an octet on nitrogen. What do you think I could do here? A double bond, right. I can coerce one of these oxygens to be so kind as to share a pair of electrons with the nitrogen. All right? So it doesn't really matter which oxygen shares the electrons with the nitrogen. We're going to be taking any pair of electrons, let's say this pair, and we're literally going to be moving them into this bond between the oxygen and the nitrogen. This arrow that I've used is something that we use in organic chemistry a lot. It's an arrow pushing type of mechanism. But we're moving these electrons from being located solely on this oxygen to being shared between this oxygen and the nitrogen. So what's that going to do? What would that look like? If I share those 2 electrons, they're now going to be in a double bond. Okay? Does that make sense? How many electrons are around this oxygen right now? 8. I haven't changed the total number of electrons around it because it's just sharing those 2 electrons with the nitrogen. So I have 1, 2, 3, 4. So each of these dashes here represents 2 electrons. 1, 2, 3, 4, 5, 6, 7, 8 electrons around that oxygen. Is that good?
Does it matter why you angled it this time? Instead of 90 degrees?
No.
I mean, is it supposed to be equal angles between the bonds? Is that what you're trying to show that.
That's what it is in reality. It doesn't have to be that way in this Lewis structure. I could have drawn this at 90-degree angles there. That's absolutely fine for Lewis structures. I have a proclivity for putting it in the right direction. Okay. How about this nitrogen now? Does the nitrogen have 8 electrons around it? Yes. So nitrogen's pretty happy. These two oxygens have electrons around them too, right? 8 electrons around them too. What else do I need to do to this molecule to complete the Lewis structure? Formal charge. All right, so let's work on that. Now, formal charge, remember, you're going to be investigating every single atom in this molecule. All right, so let's start at this oxygen here. What group number, and I'll throw up our formula. So formal charge is equal to our group number minus half of the shared electrons minus the unshared electrons. Okay, so let's do this oxygen right here on the left. What group number is that in? 6. How many shared electrons does it have around it? It has 4 shared electrons around it. All right? 4 in that double bond, 2 in each of these dashes here. So that's going to be 6 minus half of 4, which is 2, minus the total number of unshared electrons around it. And that's going to be 4. So 6 minus 2 minus 4 is equal to 0. So this oxygen here is neutral. All right? You don't need to indicate a charge or anything like that on it. Does that make sense? Okay, let's do this oxygen here on the right. Group number 6 minus half the number of shared electrons would be 1, minus the total number of unshared electrons, 6. So that equals -1. All right. So you can draw a little negative sign in the upper right-hand corner of that atomic symbol. Is everybody okay with that? All right, so a negative charge on that oxygen. Can we all agree that this other oxygen is in the same boat? All right, it's in the 6th group. It shares 2 electrons, has 6 unshared electrons around it. So that's going to be -1 as well. Is everybody okay with that? Okay. How about nitrogen? Let's do nitrogen now. What group is nitrogen in? 5th group. How many electrons does it share? Take half that number, it would be 4. Minus how many unshared electrons are on that nitrogen? 0, right. So 5 minus 4 equals a +1. All right. So we've successfully calculated all of the formal charges on each atom. All right. Does this make sense? We have a minus, a plus, and another minus on this atom.
Okay.
We're going to do a couple more examples.
Does that also tell you the number of double bonds or no?
Not necessarily. Not necessarily. That's the degree of unsaturation, I think. And we're not talking about that. So, okay. Questions on this? Does this make sense so far? Okay. Let's do carbon monoxide, CO. What group is carbon in? 4th group. So 4 electrons. What group is oxygen in? 6. So we have a total of 10 electrons. Okay. Well, only 2 atoms here, so there's not really many choices of how to put this together. So carbon is probably going to be bonded to our oxygen. All right. Again, I like to do this systematically. I might get the structure wrong at first, but at least I'm going through it in a logical way. So I've used 2 electrons. I'm going to dump in the remaining 8 electrons into my system. And I usually start at the most electronegative atom. All right, so I'm going to fill the octet on the oxygen. I've used 6 more electrons, and I have 2 more, so I'll put them on carbon. What's wrong here? Carbon's not happy. Not happy at all. You can even check yourself right now. We can calculate the formal charge on this carbon, right? What's the formal charge on carbon as drawn right here? Group 4 minus half of 2 minus 2. All right.
How do we know which is the most electronegatively charged atom?
If you look back at the periodic table, the closer you get to fluorine, the more electronegative, not necessarily charged, but the more electronegative that atom's going to be. All right, so oxygen is right next to fluorine. So it's a personal preference. You don't have to do it that way. I just like to have some sort of systematic way to go about
But if
this.
you do the other way, it's going to be wrong.
Yeah.
And then you have to find out that it's wrong.
Yeah, well, we might find out that this is wrong too. You know, so it really is system dependent. Okay. All right, so 4 minus 1 minus 2 is plus 1. All right. This oxygen here is going to be group 6 minus half of 2 is 1 minus 6, so that's negative 1. All right. But we still don't have an octet on the carbon, so that's just wrong altogether. So what can we do? We can share, right? We can move these 2 electrons down into that carbon-oxygen bond, right? And that would look like that looks a little bit better, right?
Still not doing it.
It's still not entirely happy though, right? So what do we have to do again? Share and share again. All right, so let's take 2 more electrons down and add them into the distance between the carbon and the oxygen. What are we forming now? A triple bond. All right. Do we have an octet around both atoms? Yes. All right. 1, 2, 3, 4, 5, 6, 7, 8 around carbon. 1, 2, 3, 4, 5, 6, 7, 8 around the oxygen. We're good. What do we need to do now? We have to assign formal charge. You can't talk about carbon monoxide unless you assign formal charge. So let's do the formal charge on oxygen. What group is it in? 6. How many electrons does it share? 6. Take half of that is 3 minus 2 plus 1. Right? How about carbon? Group 4 minus 3, same as with the oxygen, minus 2. That equals negative 1. Right? So we have a minus charge on that carbon and a positive charge on the oxygen. That looks kind of crazy, right? But that's right. All right? We have an octet on both atoms. We've accounted for the formal charges on both of those atoms. The overall charge on this is going to be neutral. Right? We have 1 positive charge and 1 negative charge. All right? So that's really what carbon monoxide looks like. Well, why is this important? Well, what does carbon monoxide do to you? It kills you. All right? It will compete for iron and hemoglobin. All right? And that's really a result of this structure. All right? So if we want to have more in-depth conversations about stuff like that, you have to know what the structure looks like. And you can't really get at the structure if you don't have a complete Lewis structure. And that complete Lewis structure includes a formal charge. Okay, questions on, yes?
This might be too big a question, but in the presence of carbons and oxygens, why not just something simpler like CO2?
You want to do CO2?
Well, no, I know what CO2 looks like. Why would this ever occur?
Why would carbon monoxide
Why
form?
Carbon monoxide.
Well, it's not oxidized all the way up yet. So if you're burning hydrocarbons of some sort. You know, you're reacting those carbon-hydrogen bonds, carbon-carbon bonds and carbon-hydrogen bonds with oxygen. Right? So you're going to be oxygenating those carbon atoms. All right? In complete combustion, when you fully oxidize that carbon up, you're going to be adding in, you know, another oxygen there. But carbon monoxide is not as fully oxidized up as that carbon dioxide is, or even carbonate. So there are just different, varying degrees of oxygenation. So, you know, this is a carbon that's attached to one oxygen atom. Carbon dioxide, all right, is going to have 2 on there, and then you can have a carbonate. We'll talk about carbonate in a little bit. So it's just varying degrees of oxidation on the carbon atom.
Okay, I guess I don't know why, yes. That's why it might be.
Oh, as to, well, I mean, say the oxidation doesn't always perfectly go to, you know, one oxidized form over the other. So it really depends on the conditions through which you're oxidizing the carbon.
Okay.
All right, there's going to be a lot of different answers to that, I think.
Okay.
Good question. All right, are we doing all right with this formal charge? Should we do, well, let me tell you that I've been lying to you. All right, let me come clean before we go any further. Okay, so I've told you that all these atoms want to have octets, right? That is false. All right. Atoms, let's say in the second row of the periodic table, will want to have octets. Why is that? Well, they're small atoms and they can't really access higher orbitals. But when you get to the third row, when you're talking about atoms like chlorine, bromine, or sulfur or phosphorus, right, these are larger atoms. They have access to higher orbitals where they can put these extra electrons. Okay? So we'll often see, say, phosphorus drawn with 10 electrons around it. All right, even, does anybody know what anybody know what this ion is? It's phosphate. All right? This is in our DNA. All right? We have phosphate linkages. Look at how many electrons are around this phosphorus here. 10, right? 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. All right? It's a common motif. All right? So it's not something that's, you know, totally out of the ordinary. We'll see this all the time. And so we can't ignore the fact that you can have more than an octet around an atom. But it comes with the caveat that it's got to be in the third row or larger. Okay? We're not going to see a lot of exceptions where something in the second row is going to have more than an octet around it. It'd be a pretty extreme example. Okay, so you can have this phosphorus pentachloride or this sulfur hexafluoride. All right, these are going to exist just okay. And when you're putting these Lewis structures together, that's something you need to take into account. If you have more electrons than you know what to do with, look to see if you have any of these heavier atoms that can accommodate more than 8 electrons. Boron's another exception. Boron is a compound that tends to have less than an octet. And BF3 is a good example of that. And let's go through this to really prove to ourselves that this is the correct Lewis structure for BF3. All right. So what group is boron in? Third group, so that has 3 valence electrons. What group is fluorine in? 7th group, so we're going to have 21 if there are 3 of them, right? Is everybody with me? All right. So that equals 24. The structure, as you see here, is like this. How many electrons have I used to form bonds between boron and the 3 fluorines? 6. All right? So that means I have 18 electrons left. I'm going to give those electrons to the most electronegative atoms. All right, I've used up all of my electrons. I don't have any more. But I don't have an octet on boron, right? We might say that's a problem. Well, can we do what we did on nitrate before? Can we share some electrons from the fluorine down into the boron? Well, we can try, right? You know what I mean by that? Just move a pair of electrons down here like that. All right? Let's see what it looks like. Play along with me. Play along with me. All right? If we do that, we're going to get something that looks like this. Let's calculate the formal charge on this to tell us why this is not right. All right, so if we do this fluorine over here, that's group 7 minus half of 2 minus 6. So that's 0. Means this fluorine is probably going to be 0 too. This fluorine here is group 7 minus half of 4, which is 2, minus 4. So that's going to be a plus 1. Boron is in group 3, minus half of 8, so that's 4, minus 0 unshared electrons, so that's going to be minus 1. All right, so we've gone from a molecule wherein we don't have any charge separation, all right, we don't have any charges drawn on there, to a molecule wherein we do have charge separation. Boron's going to be the exception. Boron is going to favor not having a full octet rather than sharing electrons with something else to get an octet. Okay. The consequence of this, again, as I said, structure is going to dictate what the reactivity of these things are, the function of these things. The consequence of this is that boron is a great acid. All right? Do you teach Lewis acids in your classes? Lewis acids are electron pair acceptors. All right? Boron is without a full octet. So if there's, a molecule floating around, like an ether of some sort that has free electrons, those electrons are going to be attracted to that boron and form a complex. All right? This is a Lewis acid. It's an electron pair acceptor. So that's why we need to know the structure of these things. We know how they react once we see the structure. So knowing Lewis structures and formal charge, we're able to get at that reactivity overall. Does that make sense so far? Okay. The last thing that I want to talk about are resonance structures. Checking out ESPN during class? Bless you. Bless you. All right. That's 2 sneezes. We don't get any more than 2 sneezes per class. I'm just kidding. All right. So now we're going to go into the last thing with drawing these Lewis structures. From time to time, it's going to occur that we can draw more than one equivalent Lewis structure for one molecule. So carbonate, CO3 2-, is an example of that. All right. Carbon brings 4 electrons to the table, 3 oxygens bring 18, and we have 2-. So what does that mean? We have to add in 2 electrons. So that equals a total of 24 electrons. If you look at the Lewis structures that we have here, the only difference between these structures, between 1 and 2 and 3, is the position of these non-bonding electrons and 2 of the electrons in the double bond. All right? That's one of the hard and fast rules for resonance structures. When we're interchanging between 1 and 2 and 2 and 3, we can only move these non-bonding electrons and these electrons in double bonds. Yes?
Number 1 has only 4 at the top. Is that what you're
Yes.
But it's the same as number 2. It's bond.
Okay, so the question is, aren't these the same thing? They're just sort of tilted. Well, In a way they are. But if you, let's say if we labeled one of these oxygens with an isotope or something like that, then they'd be different. But wait till I'll wait till I fully explain this and let me know then if you still have a question. All right. The only difference between these is just the position of those electrons, right? But you can say that they're rotated. I see what you mean, and I'll explain that in a moment. Okay. The way that we interconvert from or between these structures is, again, only moving these non-bonding electrons and electrons in the double bond. So again, I'm using these arrows to indicate the movement of electrons. So 2 of these electrons will move into the space between the carbon and the oxygen. Carbon already has an octet here, right? So I need to displace electrons when I do that. All right, so that would interconvert 1 to 2. I form a double bond here. I break the double bond here. Okay? And then I can interconvert 2 to 3 by moving these electrons into this oxygen-carbon bond space and then displacing these 2 electrons onto the other oxygen. I haven't touched the connectivity between these atoms. I've only moved the non-bonding electrons or the electrons in the double bond. All right. Now I know what you're saying. This looks like I'm just rotating these molecules. But if we looked at what the carbonate atom really looks like, if we were able to take an X-ray picture of this carbonate atom, you might expect that we'd see an unsymmetrical molecule. We would see a picture wherein we'd have 1 carbon-oxygen double bond. And carbon-oxygen double bonds are shorter than carbon-oxygen single bonds. So we might say we'd see this double bond, and then we'd see 2 carbon-oxygen single bonds, right? If you were to take a picture of that, it would look like this, right? Hopefully. But that's really not the case. When you take a picture of this compound, when you take a picture of carbonate, we don't see a nice, neat double bond and 2 neat single bonds. We see structures, this is a flame transition, we see a structure wherein there are equal bond distances between all of the carbon and oxygen bonds. We don't see differences in length. All right? And if this was an accurate picture of what carbonate really looks like, we would expect to see this bond being shorter than the other 2 bonds. But we don't see that. So we say that these are resonance structures that are imperfect depictions of what this molecule actually looks like. And we say that the actual molecule is going to be better represented by what we call a hybrid structure. And this hybrid structure doesn't have single bonds or double bonds in it. It has bonds that are of intermediate length between a single bond and a double bond. All right, so getting back to your question before, if I was just rotating these things, all right, I'd still see the length of a carbon-oxygen double bond and 2 carbon-oxygen single bonds. But if that really doesn't depict what the molecule is, that wouldn't explain why we see the bonds of this length. All right? So people used to think that these molecules would resonate between one another. That at one point the molecule would look like this, another point the molecule would look like this, another point the molecule would look like this. That's not really the case. These electrons don't resonate through this molecule to go through these different structures. Again, these are our imperfect depictions of what this actual molecule looks like. All right? Lewis structures are human-devised tools. They can only go so far. All right? This hybrid, this non-Lewis structure, is our best attempt at picturing it. Now I have on here also delta minus signs, and delta is the lowercase Greek letter, and that indicates that there's a partial negative charge on that atom. Because if we look at the resonance structures that contribute to this hybrid, if we look at all these contributing resonance structures, at one point every oxygen here is going to bear a negative charge. Okay, so in our hybrid structure, we indicate that with a little delta minus. What's the point? What's the point of showing this? The point of showing this is that, well, we have some rules here, but the overall point of showing this, sorry, you get to see the flame transition again. The overall point of showing this is that the energy of this hybrid structure is going to be lower than that of any contributing resonance structure. How do we say that? Well, if we look at these oxygens here, this oxygen in this structure has a negative charge that's localized right on that oxygen. In this structure, negative charge is localized right on that oxygen. If you can spread around that localized negative charge onto not just that one atom, but onto the other atoms, you diminish that charge. You lower that overall energy of the system. It's like a game of hot potato. So if I took a 450-degree potato out of the oven and I threw it at you, you'd want to let go of that real quick, right? You'd pass it to your neighbor. All right, that would diminish the effect that that hot potato has on you. Same thing with an electron. All right, if I tossed an electron at that oxygen, wouldn't want to hold on to that for so long. So you can spread the charge out across 3 oxygens rather than localize it on just one oxygen. All right, and that's what we see when we take a picture of this molecule with an X-ray. All right, we don't see these individual resonance structures. We see something that's better represented by this hybrid structure. Even if you look at an electron distribution map of this, you're going to see equal distributions of electrons around those oxygens rather than an unequal distribution that any of these structures would show you or would tell you to expect. Does that make sense? So going back to the NO3, and I think that was an example that somebody had asked me. We can draw resonance structures for our NO3 ion. Instead of having the double bond right here, we can have the double bond occur between this nitrogen and either of the other 2 oxygens. All right, am I done? Can I draw another resonance structure for this? Yeah, good. All right, I can move, let's see, where haven't I done it yet? I can move these electrons up here like that. When you do this, be careful not to change anything else in your molecule. You're only moving those non-bonding electrons and those electrons in the double bond. Okay? So there are 3 valid resonance structures that we can draw for the nitrate ion. We can also draw its hybrid, right? If we were to do that, positive charge is always on the nitrogen. We're alternating. We have bond lengths between a double and a single bond. Right? We're going to have our partial negative charges on these oxygens, and you can draw in the electrons on these oxygens that don't move. Okay, so that's a hybrid structure for the nitrate ion. All right, that's more in line with what that ion actually looks like than any one contributing resonance structure. Okay, so what have we done today? We started off by talking about valence electrons and the octet rule. We've used them to take a molecular formula, put together some sort of Lewis structure. We did that for a couple of easy ones, and then we looked at formal charge. That told us where the electron distribution was in the molecule, whether if you had an electron deficient center or an electron rich center. All right? And then we went and used that to talk about resonance structures, where you can draw more than one valid Lewis structure for a molecule, and how those resonance structures were our best approximation to look at a molecule using Lewis structures, but are imperfect in and of themselves. Do you guys have any questions for me? On Friday afternoon, we're going to talk about 3-dimensional structure. All right? You guys have been great. I really appreciate it. I hope you have a good rest of your afternoon, and I will see you on Friday. If you guys have questions, please let me know. I'll be around. Okay? Thanks, everybody.
Thank you.
Oh, no, I'm going to keep it up there.